Hi, I am Jun Manahan, and today we'll be discussing about an algorithm or a machine learning technique called k-means clustering. So let's proceed with the presentation. So for the breakdown of the slides, we'll be first discussing what k-means clustering is, and then we'll provide a methodology on how to do this test. We'll support the definition of the technique by citing an example, and then later on discuss the pros and cons, and then the applications on where we could use this kind of technique. So first, k-means clustering is a method of vector quantization that aims to partition a number of observations into k clusters. So what this essentially means is that this method uh, is aimed on creating a partition or a group on a seemingly random data. So the objective is to make a sense of a random points or random observations that could later be used for the next steps or next steps of analytics. So it works by dividing the large set of points or vectors into groups having approximately the same points closest to them. So we will be using mostly distance calculations in determining which clusters or which groups a certain point should belong to. Again, this is designed to cluster seemingly random number of observations into bins or to clusters or partitions. And then also it's important to note that k-means clustering is is a type of unsupervised learning, meaning we're not after a particular problem to solve. We're just trying to make sense of a seemingly random data. Uh, the objective of k-means is simple. It's to group similar data points together and discover underlying patterns. So as mentioned earlier, it's unsupervised type of learning. So we're not actually trying to solve a particular problem. We're just trying to unveil a pattern within that data. And then, as mentioned, we will be using distance calculations using Euclidean or rectilinear. And then it's important to note that the number of clusters or the groups has to be determined beforehand. So before we proceed with the next steps. And since this is an iterative process, so meaning the calculations loops back on itself until it finds out the optimum value. Um, there's of course criteria on where or when to stop. So it's either when if we arrive at the situation where the centroids have already stabilized, meaning the distances between the centroids and the points are not changing, or the defined number of iterations has been achieved. So for the methodology, of course, we have to load the data in a table format in either in Excel or in a Python or R. And then we have to define the k or the number of clusters where k should be less than the number of observations n. Next is we have to define the starting centroids. Again, this is not highly critical because this could actually be user defined because this will iterate anyway. So the centroids will change for each process loop. And then of course we have to calculate the distance between the centroids and the data points. And then once we have calculated that distance calculation, we will assign the cluster based on the result. And then after that, we will loop that process in until we arrive to the optimum result. So as an example, we have here a data containing 10 observations. So we have plotted there here on the XY graph on the right side. Step two will be to define the k or the number of clusters. So for this example, I've used k is equals to 3. Again, we could use different values of k. Uh, Values of k. So it's just that it has to be less than 10 because it cannot be more than the number of observations. Next is to define the starting centroid. Again, this could be at random, so it's doesn't have to delve much into the determination of the initial centroid. So for this one, I've decided to use the centroids from points 5, 6, and 8. So we will be using that as our starting centroid. So we will use those xy values. So x equals to 7 and x equals to 9. Uh, x equals to 4 and y equals to 5 and x equals to 7 and y equals to 3. Step 4 is to calculate the distance between the points and the centroids, the initial centroid. So the distance formula is simple. It's the absolute value of the difference between x1 and x2 plus the difference between y1 and y2. So if we do that in the first point where the value is x equals to 10 and it's y equals to x equals to 8 and y equals to 10, we will have a value of 2. And then if we do that in reference with the second centroid with a value of x equals to 4 and y equals to 5, we will have a value of 9. And for the third centroid, we will have a value of 8. And then we have to define the minimum value of that calculation. So for this case, the minimum value is 2, which falls under centroid 1. So we will tag this point as a member of cluster 1. And then we repeat this process throughout the whole observations, and we will come up with this table. So uh, point number 2 will have a value of 4, 11, and 10. And since the minimum value is 4 and it's under centroid 1, we will put it as cluster 1, and then so on and so forth. And then we will have this summary. So cluster 1 will be points 1, 2, and 8. Cluster 2 will be points 6, 7, and 9. Cluster 3 will be points 3, 4, 5, and 10. If in case that there is an equal distance measurement, any of the points could be chosen. So it's not the critical. So if there's a value that is equal, for example, the distance is 0 and 0 for cluster or for centroid 2 and centroid 3, you could choose either. So it doesn't matter anyways because for the next iteration, the centroids will change. So if we have to recalculate the centroid as part of the step 6. So the way we do that is we get the value of the clusters, the x and y values of the cluster. So for cluster 1, the value of x equals to 8 and y equals to 10, x equals to 10 and y equals to 10, and x equals to 7 and y equals to 9. So we just have to get the average of that. So the new centroid for centroid 1 will be x equals to 8.33 and y equals to 9.67. And we do that as well for cluster 2 and cluster 3 until we arrive to the new recalculated centroids. So we'll have to use that new centroids to calculate the new distance for the new distances from the points. Doing so, we will arrive at the new clusters. So cluster 1 will remain unchanged. So cluster 1 are points 1, 2, and 8. Cluster 2 has changed. It only now has points 7 and 9. And then cluster 3 has the values 3, 4, 5, 6, and 10. Again, we will recalculate the centroids by getting the average of the new of the values per cluster, and then we will arrive at the new centroid. So cluster 1, centroid 1 remains unchanged, and cluster 2 and cluster 3 has changed. So we'll use these new centroids to recalculate the formula. So again, employing the same calculation using the distance measurement, we arrive at this new clustering. So cluster 1 remains unchanged as well, 1, 2, and 8. Cluster 2 has changed. It only has now the value of point 0.9, point of 9. And cluster 3 is points 3, 4, 5, 6, 7, and 10. Again, we will recalculate the recalibrated centroids using the new values, and then we will arrive at these values and then punch that into the table, and we will arrive at this cluster, then the new cluster. So cluster 1 remains unchanged, 1, 2, and 8. Cluster 2 is also unchanged, 9, and cluster 3 is unchanged, 3, 4, 5, 6, 7, and 10. So at this point, we have the same clustering from the previous iteration. So as if you remember earlier, the criteria is that we have to stop once we have reached an iteration or the clustering that is the same from the previous one. So we can call this as the final clustering. So just to review the evolution of the clusters, this is from the first iteration, the second, and the third and the fourth iteration. So we have stopped at the fourth iteration because the values of clusters from the third iteration and the fourth iterations have not changed. So to have a more visual look, so this is the clustering that has happened from the first iteration to the second and third and fourth. So you could see here that the clustering has not changed from the third to the fourth iteration. So this is where we decided to stop. So what are the advantages and disadvantages of this? So number one, it's very easy to understand and implement. We're using basically simple mathematics for distance calculation, and also in the recomputation of centroids, an instance can change the cluster. So this will basically recalibrate to correct our calculations per each iteration. So the disadvantages is that it's a bit difficult to predict the number of clusters because, as mentioned earlier, if the data is very random, it's very hard to assess how many partitions that is sensible. And then the output is strongly impacted by initial inputs by the number of clusters. Again, it's because it has to be user defined. And then the order of data will have strong impact on the final output, yes. And then it's not good in doing clustering job if the clusters have complicated geometric shapes because we're talking about centroids, and having shapes that are highly complicated might skew the results of this method. So some of the applications of the k-means clustering is, and the first we have to review the objective of the k-means clustering is to get a meaningful intuition from the data we are working with. So get a sense of of seemingly random information, and then predict groups based on the means or the mean distances from the centroids of the data. So for applications, we could use this for document clustering, image segmentation. So we're actually using this to, we could actually use this for text recognition as for this example, image compression, and customer segmentation. So I guess that's it for me. Hopefully, the idea is clear on what k-means clustering is and how do we perform this test and where should we apply this. So thank you.